So let's talk about thermodynamics. So the first law of thermodynamics suggests that energy is never created or destroyed. It's just converted into something else. And that's really kind of something we can think a lot about as we thought about our walnut that we burned. Because we know that if we take a walnut and we burn it, that it's actually releasing energy. We knew that because that energy was then used to heat up that water. And so this burning of a walnut is what's called an exergonic, or a spontaneous reaction. It's actually releasing energy. So we can see this graphically because we can see along this bottom axis is actually time. So as time progresses, we know we start out with a walnut with lots and lots of free energy, okay? And as we burn it, it actually reduces the amount of energy, and a lot of energy is actually released. You're probably also going to notice that there's that little bit of hump where you actually have to go up in terms of energy, and that's what's called the energy of activation. And so you actually have to put a little bit of energy in to be able to make this process go. And of course we know you had to light the actual walnut on fire to actually make it actually burn. And so this is an exergonic relationship, or a reaction where you're actually releasing energy through this process. And it's spontaneous. It will, for the most part, just happen on its own. The opposite of this is what we saw when we actually heated the water. So we started out with very, very low energy with our cold water, and we actually had to put energy in to actually increase the amount of energy. This is what's called endergonic. And so you're actually having to put in energy to actually make it progress. And so this is a non-spontaneous type of reaction. You actually have to invest the energy to make it proceed. And the really neat thing about biology is that in many cases you can take these two different types of reactions, exergonic and endergonic, and do what's called coupling them. So energy coupling is when you take these two pieces together. So we can see we have our food item here, which we talked about. That walnut in our case was pretty high in energy, and we burned it. In this burned food, of course, we know we had less actual mass, and some of that energy that was lost, of course, some of it was actually lost and was inefficient because of the system we had, but some of it was indeed transferred, if you will, over to the water, which allowed for our cold water to then become warm. And so we know that the first piece of just simply burning the food, just taking this high energy food and burning it, is what's the exergonic reaction. So it's actually releasing energy. And then the right side is this other piece, which is the endergonic reaction, taking cold water and actually applying heat to make warm water. And so that's the endergonic reaction. So energy coupling is simply taking these two types of reactions and putting them together. And that's all kind of reliant upon this kind of central energy transfer that's here in the center. And we can do this with all sorts of things. So we can take this kind of empty box reaction and just fill things out. And it can be any types of reactants, which starts out some reaction, and then products, which actually ends it. And we know that these two boxes are always going to be the same thing. We always have some energy lost. Even if we have the most, what we think is efficient system, we're always going to lose energy. And then hopefully we're going to have some energy transfer. If we don't have some, then we're never going to have coupling. And we can change this to anything we want. But we know that this side is always going to be our exergonic because it's releasing energy, and then the right-hand side is always going to be endergonic because it takes or it uses energy to be able to proceed because it's not spontaneous. And so we could use an example like, say, the fact that you use gas to power your car. And so we know that for the exergonic reaction, you're actually having gas, and you take gas that's high in energy and you combust it. And of course what you end up with is that CO2 exhaust, and of course what's released is energy. That energy then is used to take your stop car and make it move, okay? And so this is this example of energy coupling. Of course we can do the same thing by having, instead of a car that stopped and moved, we can have a person that stopped and moved. And instead of course having gas that's put in, we can actually have food that's put in. The interesting thing about us is that we actually have to have this intermediary, because we don't necessarily always want to be able to consume and then break down the food and then immediately be on the run, because that's not always going to work. But we need to have some way to kind of store the energy, and that's exactly what this adenosine triphosphate, or this molecule ATP, the main function of it. And so we use ATP as a way to kind of take the energy from the exergonic reaction and store it so that we can then be able to break it later, or kind of release the energy from it later and use it in an endergonic reaction. And so we can kind of think of this ATP molecule that we have here. Hopefully this should be familiar, as it looks very similar to some of the nucleotides that you've already seen before the semester. And we can kind of think of it as kind of like a dart gun, if you will. This molecule of ATP, where we have these 3 phosphates here at the end, and they each have this little negative charge right there. And those negative charged phosphates kind of act like these magnets that really want to repel each other. And so that when you finally are able to kind of take that one phosphate at the end and release it, it's going to release like a spring and kind of shoot off the end, releasing a whole lot of energy. And then you're left with this ADP. The D stands for diphosphate because there's only 2 phosphates at that time. So then to get that 3rd phosphate and put it back on actually takes a significant amount of energy. And so you can then see kind of how this all works, where we are actually able at the far left-hand side taking our food, whatever kind of food it is, and we're breaking it down into our digested food. Of course, some energy is actually lost. A lot of it's actually transferred into making the ADP and ATP. And so that first reaction is exergonic, is transferring that energy. The second one, going from ADP to ATP, is endergonic. So that's kind of the first coupling that we have. And then maybe at some point later on, we're ready to kind of have our body start working or do whatever we want to. And at that point, we actually take the ATP and are able to kind of cleave off that lost phosphate. In the process of being able to break off that lost phosphate actually releases a tremendous amount of energy to then allow our body at rest to be a body in motion. So of course, breaking ATP down into ADP is exergonic, and then having that energy transferred from the body at rest to a body in motion is endergonic. And so that's kind of a stepwise how we can couple all of these different types of reactions so that we can have the timing be actually uncoupled, and we don't have to actually digest the food and be able to have it allow us, our bodies to be able to move all at the same time, and is actually using this molecule of ATP as a way to kind of store that energy so we can use it whenever we need it. And so that's kind of how energy and ATP work.